Right, is everyone ready for our webinar session? Okay, thank you everyone for joining our webinar. Today, we'll introduce one of Hioki's electro-resistance measurement system, RM2610, and we'll discuss the measurement methods. Before we get started, I want to do a quick rundown of our agenda. First, we'll have an introduction of our presenter. Then we'll start our presentation, which will last about 40 minutes, and we'll end it with a short Q&A session for about 5 to 10 minutes. And I just want to point this early on that we will not stop during the presentation to answer any questions. So we highly encourage you to type in your questions in the chat box. And we will not take any questions regarding product quotes or pricing during this webinar, but you are more than welcome to write us on a separate note, and we'll be happy to further assist you. Okay, so now I would like to introduce our great speaker, Chris Schultz. Chris is our newest product manager, and he comes with an extensive background. Right before joining our team, he was a product manager with RNS, where he was responsible for the Vector Network Analyzer product portfolio, just to name a few. Chris holds a PhD degree in electrical engineering and a master's degree in aerospace engineering from the Georgia Tech. A very smart guy. With that being said, please welcome Chris. Chris, all you.
Jennifer, thank you so much. Well, it's a great honor to be here and tell you a bit about interface resistance measurements of lithium-ion battery electrode sheets. Here's what I plan to do in this presentation. I'm going to give a short introduction in electrode sheet resistant measurements. I'll mention current methods, traditional methods on doing these measurements. I will introduce you to Hioki's unique measurement technique that has significant advantages over the competition. I'll give you some measurement examples for different applications. We'll show you how this tool, the RM2610, actually works, and then we'll wrap it up with a summary. Let's, by way of introduction, let's talk a bit about batteries. I assume you all are experts in batteries, so I don't need to say an awful lot there. Batteries is a fast-growing market. They are penetrating our daily life. You know, anything that is not connected to the wall has a battery built in. I want to highlight three applications. Automotive. Batteries have always been part of the automotive electric system and starter motors, but there is a lot more going on with batteries in automotive as electronic permeates into everything automotive. A big part of the automotive industry is going to lithium-ion batteries for well-known reasons. That is the power density that lithium-ion is just very good at. They are light, they are adjustable, they're compliant, so you can put them in various cavities of the automotive body. So a lot of advantage of going to lithium-ion for automotive applications. Another application that's very popular is mobile devices, body area networks. You know, cell phones have been using lithium-ion batteries for a long time. There have been well-published issues with lithium-ion batteries that exploded in mid-flight. You know, that's obviously something that, as battery manufacturers, you want to avoid by all means. You have to avoid by all means. And again, that's where testing comes in. Body area networks are becoming a big thing, where it's not just a cell phone. You know, cell phone is really a communication platform. We're talking about 5G. Where you're in constant contact with the network, sending data, making the life a better place to be. Body function monitoring, which is certainly an important aspect of the epidemic that we have going through right now. So I would think that there will be a tremendous amount of development in this area. You know, everything that you carry on your body has to be powered by some form of battery. Lithium-ion is the technology of choice there. The third application I want to mention is stationary backup power and solar power. Many applications there, legacy applications, are using lead acid. The industry is changing to lithium ion or NiCad just because of higher power storage and higher capacity. Solar is becoming proliferating here in the US more and more. It's a slow ramp. Backup power. We want to guarantee that hospital equipment is powered until the diesel generator or whatever backup generators you have is kicking in. Same thing for communication equipment. Cell towers have a tremendous amount of backup power so that in emergencies the network does not go down and keeps being up, at least for emergency responders. Lithium-ion batteries have tremendous advantages. I mentioned this already. The high energy storage density, the high energy density is probably the most important one. Lithium ion is also very low in self-discharge, so you can store the batteries on the shelf or in storage or in an emergency room as a backup for a long time. That always has tremendous commercial applications. Lithium ion is low maintenance, and you set them and forget them. You don't need to top them off with fluids, self-sealed. They are small and light, so anything that moves, size, weight, and power is important. The lighter it is for the same power density, the better it is. I mentioned body area networks already. So lithium ion is becoming the tool of choice there, and they have a very long service lifetime. So it takes a fair amount of recharge cycles before you have to replace them. Disadvantage of lithium ion: they're expensive. They're still expensive. It's a involved manufacturing process. I get into this in more detail in one of the next slides. Cost will come down eventually, but it is a relatively complicated manufacturing process. They do need circuit protection. Overheating is a real threat. Explosions and batteries that catch fire in mid-flight. There's no well-documented cases, but I'm sure there are cases where we have less documentation. So protection of the lithium-ion cells is very important. And then, of course, transportation. How do you transport them? You need to have special precautions to transport lithium-ion batteries. Every time you enter an airplane, TSA requires that you don't have lithium-ion batteries in your hand or luggage. I don't know a lot of people comply with that, but that's the state of the affairs today. So here's a slide on what the manufacturing process of lithium-ion battery looks like. It is a multi-step process with a lot of potential failure points. It starts with a slurry that contains the lithium material, other material that gets deposited on electrode sheets, copper or aluminum typically. There are other technologies out there that are actively researched, and various startups are working on alternative materials to get more compact form factors for the batteries. The sheets are coated and pressed, then cut and stacked. Metal tabs are welded on the cells. That's a whole different topic of testing. We can talk about that in one of the next seminars. Just the welding and making sure that you have good contact, and talking about milliohms and maybe microohms can be very important. The cells are vacuum sealed and dried. Next step is to fill the building blocks with electrolyte. That's when the batteries become actually operational. They get discharged and cycled and aged before they actually hit the shelf. The cells then get tested, electric tested, depending what kind of product you have. If it's consumer product, of course, there will be less testing. If it's a mission critical product, there will be much more testing going on. Finally, the individual cells are packaged into modules, tested again, and then shipped to the customer. So this is in very broad terms the manufacturing process. All of these steps have a variety of weak points, potential failures. What I'm concentrating on here in this presentation is the first and the second step. The reasoning here is that the earlier you detect issues with your material, with the electrode sheet specifically, the earlier you can make sure that your final product is not going to get shipped. Meaning you save a lot of money in sorting out bad sheets early on in the process versus trashing the whole module at the end of the production line. That's where we are in, that's what this talk is going to be about. So mostly talking about research, development, and production testing, incoming inspection. Looking at the slurry, the base material of the lithium-ion batteries, there are mainly three components in there. One is active material, that's the lithium, including lithium, conductive additives, and polymer binders that make up the slurry. It's some gooey mass that basically that's where the magic is. Now, having these three constituents, obviously you can do a lot of optimization depending what kind of cell you have, what targets you have, what applications you have. You can balance lifetime versus power density, current density. So there are a lot of things that the manufacturers are doing to optimize cells for specific applications. The active material obviously provides the current or the voltage that the battery ultimately delivers. A conduction path makes sure that the electrons can flow freely, not too freely, from one point to the other. Issues that can happen, though, if you don't have a good process control or if you have maybe too much of one constituent, that you have isolated active material. That's really not doing anything, that doesn't contribute to the battery, so you want to avoid that by all means. The other extreme is if you have clumps of active material somewhere embedded. That is not good. That can give you hot spots. That can give you that is one potential for explosions or fire in the battery. So you want to, by all means, avoid these kind of clumping. It's very difficult to detect that without an in-depth chemical analysis or optical microscopy. The tools we have will aid you in making sure that you have a uniform material distribution. Now, the next step, the electron sheet fabrication. The slurry is applied on typically a metal foil or a conductive foil, mostly aluminum and or copper. The solvents that carries the slurry gets evaporated so that it forms a what's called a composite layer. Then the sheet is pressed, typically with metal rollers, to compact the composite layer. This gives it both mechanical strength. It also gets rid of air bubbles or any inclusions that may have been included when you deposit the slurry on the copper foil. So things that are important this process step are the uniform, or the thickness uniformity of the electrode sheets. You make sure that there are no air bubbles included. Air bubbles are always a point of failure for the batteries. The material that's on the slurry, the slurry gets stirred. The materials need to be well dispersed. You don't want to have any hot spots or bunching of materials anywhere. You want to have a uniformly isotropically distributed way of material. And any mechanical engineers knows that it sounds pretty trivial to roll it with a metal roller, but a lot of things can happen when you have a metal roller hitting some gooey material. So again, a lot of potential failures in the very early steps of the battery processing thing. Now, our tools aid you to detect these potential failures and remedy them or pull them out of production, adjust your production line if necessary. So what kind of tests do you have? And we're talking about electrical tests here, right? Hioki is an electrical testing company. Now, traditional tests that have been done are using a simple tester with 2 probes. You have a very sensitive ohm meter that can measure typically into milliohms or microohms. And it's as simple as taking 2 probes, putting them on the conductive layer and measuring the resistance. If you know what the resistance should be, then you can compare it with what you get and see if there's any issue. Problem with this method is that it's very difficult to get repeatable data. Typically, these measurements are depending on the operator, how hard you press the probes onto your material, what's the consistency of the material. The probe tips wear off after a while. There are typically significant differences in operator skills and expertise. So you can get a broad variety of measurements for the same material, really. That method is difficult to implement it's easy to implement, it's difficult to make it work in a production environment. The next method that's commonly applied is to squeeze the electron sheets between 2 conductive pins or cylinders, apply a current over that sheet, and measure the voltage drop over the sandwich layer. That works pretty well. It is reproducible. It's you can automate that pretty easily. Challenge with this method is that it is very difficult to calibrate out wiring resistance and contact resistance, and we're talking about fairly low impedance measurements here in the millivolt or microvolt range. So all the cables, all the connectors, all the contact resistance becomes important and becomes an influence factor of the measurement. Now, to avoid the issues with cable resistance and contact resistance, you can apply the 4-probe method. 4-probe method works in the following way: that you have 2 probes that apply a current over the materials under test, and you use a second set of probes with a voltmeter that measures the voltage drop over a certain distance. It's a very common method applied to all sorts of applications, and it works very well. Now, for batteries and for electrode sheets, the problem with this method is that you really just measure the surface resistance, or a bit of a penetration into the material, the resistance that penetrates a bit into the material. There is really no way with this method to measure the whole material, including interface layer and the conductive sheet. So you get some information, you eliminate some of the issues with the other methods, but you still get a very limited amount of information through this method. So that's where Hioki started. Right. So, and Hioki is a bit of a different company than many other test and measurement companies. It's instruments that we build are purposely built to address specific problems. So we know the problem. This problem has been well known, and our goal was to build a test instrument that can measure resistance separate for composite layer and interface layer. The other thing that industry told us, our customer told us, you have to do these measurements over an assembled electron sheet, including the composite layer and the interface layer and the collector layer. So you cannot peel them apart or anything. That's just not acceptable in what our customers want. So we built the first prototype in 2015. That was built in Japan and Korea. We showed this to a variety of customers. In general, they liked it. We sold this product on a sample basis to our customer base. We improved the product. In 2019, this product has been fully qualified and was ready for volume sale. We started doing the first international sales and introduced the RM2610 into the American market just in 2019. So it is a mature product from the technology perspective. It is a new product that's just been introduced from the product market introduction. So really exciting times, and I'm excited to be part of that. So here's what this instrument looks like. It is a fixture where you put the electrode sheets in. It's a measurement tool and software that controls the whole thing. And I'll get into this in more detail in one of the next slides. But I want to highlight the advantage of this test approach first. So what you can do, and applications, I see three types of applications for that tool. One is for research and development testing. Folks like yourself who build electron sheets. I mentioned that you have a bunch of variables to play with: the constitution, the material types of materials, the relative amounts of materials that you put in your slurry, the consistency of the slurry, the roller pressure, and probably 25,000 other things that you need to consider when you're actually building electron sheets. So we can use that tool actually to understand if you met the goal very early in the process. You don't have to build the whole battery to understand if you will have a successful product at the end of the day. That's what this tool is about. That's what this tool helps you. So you can find the best composition of your slurry right in the early stages, and you can understand the influence of the material on the conductivity and on the resistivity of the overall electrode sheet. And again, you can get the influence on the different layers without having to peel it apart. That's a very powerful tool for research and, of course, for product development. For quality control and process control, incoming inspection, it's very easy with this tool, and I'll show you some measurement examples in one of the next slides. It's very easy to use this tool and inspect how uniform your electrode sheet is when it comes in. You just do a few measurements, do statistical analysis, and you have a very good view on how well your manufacturing process is. If you're a manufacturer of electrode sheets, how well your manufacturing process is under control, if you meet all your target specs, or if your process drifts out of control and you have to adjust some of your production machinery. It aids you in clump detection. It doesn't give you specific clump locations, but the tool can show you when your process is out of whack and when the resistivity, the local resistivity of your electron sheet is not within the spec that you set. And again, it's really an enabling tool for statistical process control. So in an SPS environment, that would probably be one of the first tools that you have and that you use to monitor how your process is, if your process is drifting, or if you're well within the control limits that your process requires. Who's interested in that? In that type of testing, I see mostly three types of applications and manufacturers. They are the material suppliers, material manufacturers themselves. If you are one of them, please, we would love to talk to you. I think we have a real story to tell you. Battery manufacturers, obviously. Right? I mean, if you build electrode sheets, then that is the only tool that gives you a one-shot assessment of how good your electrode sheet is. And we see a lot of interest in this kind of tools from automotive OEMs. That's been a big success for us so far, and we definitely want to expand on that success here in North America. So here's a bit more on how this measurement works. It is based from the mathematics perspective, it's based on an inverse analysis. Right? So you have the inverse analysis means you have the result and you calculate what causes the result. What we are doing Very similar to the four-probe method or four-point method, we apply a current over the composite layer. But instead of just probing with one voltage probe, we have multiple voltage probes that probes the whole surface area of the electrode sheet. That gives us a tremendous amount of information that we can use to do a detailed analysis. Out here on the right-hand side, you see what the fixture looks like. Right now, we are 64 probe needles that are used to measure the electric field on the surface. So with the field that we measure, the potential that we measure on the surface, we calculate the field distribution that would be the reason for the measured electric field. Next thing is we compare the calculated electric field with the ideal or with the electric field that you would expect. And based on that comparison, we can calculate the resistivity of the composite layer and of the interface layer. So basically, as I said, it's an inverse method. We measure the effect and then we calculate the cause compared to the theoretical model and then adjust our model until the model accurately predicts the result that we're measuring. And I hope this makes sense. The nice thing about this method is that as a user, the only thing you need to know is the thickness, the physical thickness of the composite layer, the physical thickness of the collector layer, and the collector resistivity. And with this information, you can calculate, based on the electric potential measurement, the tool gives you the resistivity of the composite layer. So again, here's what this instrument looks like. It is a mechanical fixture. It's on some linear stages. There's a mechanical clamp on it, and the probe pins are down in the fixture. You clamp it down. I have a video on that in one of the next slides that shows you how easy it is to use. It's really foolproof. Went through a bunch of iterations. We have a very sensitive impedance meter that controls the whole thing, and then the software that gives you the results and does all the calculations on the computer that you provide. Go to the next slide. A bit more details on how the measurement works, and yeah, that's been vetted and verified in numerous cases. So the first thing is we acquire the observed potential. We acquire potential by applying a current. We measure the voltage drop over a field of probes. Then we do the modeling of what the field would be looking like in theory. We compare the ideal field with the measured field. We calculate the potential. And then we do a decision. Well, does the calculated field match the measured field, or the field measured out of the voltage that we measure on the surface? If it doesn't, we adjust the values, and there are numerical methods that guarantee conversion, all these good things that you do in applied mathematics, and recalculate, adjust the values, recalculate the field, and iterate through that process until we meet the matching criteria. You can actually select the matching criteria, how well the calculated field needs to meet the theoretical field, until we say, yes, the calculated resistivities are correct.
Okay, everyone, sorry for the inconvenience. We're working on this technical issue we're facing, but we want to go ahead and show you the video that we have for RM2610. So let's get the video started.
Okay, so I'm logged back in, dialed back in. I'm not sure if that works. So let me keep talking here. So thanks, sorry for that trouble. What you're seeing here is the instrument in operation. That showed you how to put the how to put the electrode sheet under the pins. That's really easy to do. There's some clamping mechanism that puts a defined force on that right here. Yep, that's right where it is. So you have a grid that gives you the center point. Test multiple locations. That's really easy to do. I put the lever down, just like so. Okay, perfect. Okay, so you've seen that technology. Yeah, so you've seen the instrument in operation. It's pretty much foolproof. Software doesn't require you to go through any of the math. It's really well done. You know, what I started describing here was the math of the idea of converting from the measurement result to actually identifying the different resistors, and that's straightforward. Let me real quick give you this example here. That's an application case, process control. In this case, we're looking at the electrode density in gram per centimeter square. So resistivity versus electron density, and that's one of the parameters to optimize. The cross line here is the interface resistance. The full squared are the composite resistance. Interesting to see is that the interface resistance goes on a different curve than the composite resistance. You also notice that there's a sweet spot here somewhere 2.2 where the resistivity doesn't reduce any further than what you have at 2.2. So a very powerful tool to optimizing your process. Material composition, really the only tool that really lets you determine the material composition or evaluate material composition at an early stage at the electrode sheet stage. What I'm showing you here is two different materials. One is a traditional aluminum foil, then there's another material, the red curves with a carbon-coated foil. And again, I'm plotting the composite resistance and the interface resistance. And you can see that the carbon-coated material have a significant advantage what interface resistance concerns, but there's not a huge difference between the composite resistance. And again, so you can play with your relative material, with your relative additives, and optimize your process to meet certain specific targets without building the whole battery, which saves you a lot of money and most importantly, saves you a lot of time in the development process. I mentioned process control. This tool is very good for process control. What we're doing here, we have a electrode sheet, and it's lithium cobalt oxide, aluminum substrate with certain thickness, a certain weight, certain density. The details are not really relevant for what I'm trying to tell you here. So we're measuring the same sheet at 6 locations, A, B, C, D, E, and F. And for each location, excuse me, for each location, we get a composite resistivity and an interface resistivity. And you see that there is a certain spread between the resistivities. Now, point F has the highest resistivity, and point B has the lowest resistivity. For the composite resistivity, interface resistivity, interesting enough, is different, right? You have the highest resistivity at point B and the lowest resistivity at point F. So that gives you a tremendous amount of information over your process, how much your process spread is over a sheet or from one batch to the next. And again, as you see in this example, the composite resistivity and the interface resistivity don't necessarily go in sync with each other. So again, very, very important information on process control. So you've seen the movie already, the usability of that tool. It is a very well-built, easy-to-use tool that really you can give this to an operator, and with a little bit of training, they can produce repeatable, reliable results every single time they use it. So with this, I'd like to wrap it up. In spite of the technical challenges we had, the RM2610 really is a tool that gives you a wealth of information, wealth of valuable information when you're talking about electrode sheet resistance measurements. Right? It's applicable for research and development, where you work with your material composition, where you work with your process controls, or where you develop a process. It is invaluable for quality control, incoming inspection, quality control of materials, and gives you a wealth of statistical information when you do statistical process control. Now, the RM2610, that is the only instrument on the market that can give you both composite layer resistivity and interface resistivity at the same time with a single measurement, and without any mechanical manipulation that you need to do with other methods. It has a high rate of repeatability. It is easy to use. And again, it's a mature product. It's well established in the battery manufacturing industry. With this, I want to point you towards our corporate address. We're out in Plano. If you need more information, please call us. We have a wealth of information on YouTube, Facebook, and Instagram. Look forward to hearing from you. And with this, I'd like to pass the word back.
All right, thank you so much, Chris. Now it's time for Q&A. I believe Now-san will answer a few questions. Now-san, are you ready to answer some of the questions for all of us?
Yes. So I got 2 questions. So one question is, does your model assume uniform properties for the bulk and the interface? So the answer is yes. So we are using the finite volume model for the calculation of the voltage distribution. And second question is, what is the lowest current injected current we can supply while keeping some accuracy and without damaging the UUT? So the lowest current is 1 microamp, and to find out the best test setting, we recommend alt range setting. So the alt range setting enables us to find out the best test setting. So yes, we can test the electrode sheet to in the best setting using the alt range mode. Thank you.
Okay, any other questions that we have time for?
Okay, let me see.
For those of you who are not familiar, now is actually our product manager representing the West Coast. Very knowledgeable.
So I get this new questions. So the question is, can you measure both one-sided and dual-sided coatings? So yes, our meter can do, our system can do both the coatings. So the fixture is comes down towards the electrode sheet. So basically, the test is performed on the one side. So first, you measure the electrode sheet on the one side, and then move on to the another test on the other side. Okay, and so another question is, can one control the amount of force applied to the coating during the measurement? So the fixture has some weight, and the amount of force is determined by the weight. So usually the same the amount of force is applied to the coating.
Okay, I think we're pretty good with the Q&A session. Should we wrap up? Now, and Chris, are you guys good to wrap up?
Yeah, I think that's good. I mean, I don't see any other questions here. So maybe we'll say, if there's any other questions that come up while you're thinking about the video, or whatever, you send them to us. We're happy to answer as soon as we can do that. Yes, I sent you my email address and Nao's email address. We're always welcome to call you on the phone directly.
Perfect. Well, we want to thank you, everyone. We really appreciate you taking out your time to attend. There will be a short survey, and if you guys can just give us your honest feedback, that will be wonderful and very helpful for us to host another informative webinar. Thank you so much. Everyone be safe and take care. Thank you for attending.